everybody. Thank you very much for joining. I am Dominik and I'm super excited to be here on this live stream with Joran, the CEO and founder of Tiger Beetle, and also the one who introduced me to deterministic simulation testing. Hey, Joran.
Hey, Dominik. I'm also so excited. I think we were working out we do this once a year, and it seems like it's always a February, and now I think it must become a thing. So it's always so nice to chat with you. And yeah,
Up to this point,
that we could
we
organize.
just in the preparation, we just looked, when did we do this last time? And it was February, right? So up to this point, it wasn't planned, but from here on out, we should probably plan that.
Definitely.
All right. And then today's topic is, of course, deterministic simulation testing. So that's also reflected in this live stream's name, the Deterministic Dojo. And as I said, you introduced me to the concept of deterministic simulation testing. Up to that point, I was actually not aware of deterministic simulation testing and where it has been used in the ecosystem up to that point. So maybe it's like you can kick it off by telling everybody how you got into it.
Yeah, sure. So I should start by saying it's this principle of determinism, and it's so powerful because if you think about, just take a step back and think how you make things, and you apply determinism into the mix. I don't think Tiger Beetle would be here today if it wasn't for this. And it was touch and go. So it was July 2020. I was designing Tiger Beetle, and up till this point, I realized, this year I turn a certain age, which means I've been coding for 30 years. And I think most of my journey in coding was, okay, let me learn how to code. And I wrote, BASIC, and it was, and you could do things there with cos and sine in those early days and build. It was actually a flight simulator. That was one of the first programs that I made. It was like a graphical simulator of a plane. And then, but most of like the time of being a coder was like coding. And then along the way, it was like, well, you should write tests. And now it was testing. And in the few years before Tiger Beetle, I was doing some very difficult projects that were distributed. So they were running software, a program that runs across machines. And I kept failing and failing and failing. And then I wrote like a simulator that could simulate the program running on real machines and try and break things. There wasn't determinism, but there were also early parts of Tiger style that we use in Tiger Beetle with assertions and various techniques. And finally, like the third version of the system, it worked. And then it really worked. But that was coming into Tiger Beetle. So there was learning how to code. There was learning testing, like unit tests. I did a lot of like fuzz tests. It wasn't always enough, just to fuzz individual modules of code. And then there were elements of Tiger style in this pre-Tiger Beetle project. And there was the idea of a simulator. So, you've gone from coding to testing to simulating, testing, simulating. And then in July 2020, there was this, of course, we're gonna do fuzzing, and it's a simulator. It's like chaos engineering, like Jepsen. You've got a harness. These are very powerful things. Also, because you realize that the hardest part of building a difficult software program isn't the coding, like I used to think. It's actually the testing. That these systems are very hard, and so you spend so much time testing them. And so coming into Tiger Beetle, the thing there was, how can we take a step back and think about how we think? How can we engineer the engineering? And I happened to read this blog post by Sujay Jayakar at Dropbox on the testing they did, and they were bringing in more determinism. So not only simulating, but simulating the whole system in a repeatable way, so that a given simulation, it's like the Worms, the game, or Scorched Earth. The levels for those games were randomly generated from a seed, but if you had the same seed, you could generate the same game, And so this whole idea is not only to simulate, but let the whole simulated environment spring from a little number, and like a big bang, and it all goes out. And so they were doing this at Dropbox, and so I thought we should do that, because my previous experience was, if you have these simulators, it's very powerful, but it can take you, you will find a bug, but it can take you a year that the bug is there, that you have to fix it. And so, yeah, Tiger Beetle was kind of the next step, where it's like not only testing, not only simulation, but this principle of determinism. And that's how I got in. But how about you, Dominik?
I had some, like, I was like just listening, right? I can hear some similarities and parallels. So, and I also realized how old I actually am, because I'm also like on this journey for about like 30 years. So
I actually thought you've got more experience. Yeah, okay. Yeah.
I also started with BASIC. So, but so when I started my career, and say the starting point of like the serious part, right, of the career, when I joined SAP in Silicon Valley in 2008, I was just excited, right? So it's like I was just excited, and I was like, any young engineer, just like run, right? But over time, I became frustrated. Like run was not enough, because with every step I took, I also kind of realized and understood what I don't know, right? And that, I think, is on this like experience ladder. When you climb the experience ladder, right, at some point you think, I got this, right? I have it all in the bag, and then you take a few more steps, and then you come to the realization, oh, I don't have this, right? So, and that was then especially true when I moved into distributed systems, which when I joined SAP 2008, that was the year, or in 2006 was the year the cloud came about, right? So it's like I started my career with the cloud in lockstep. And with the cloud in lockstep, that basically means that it's like every system is a distributed system. And at some point, it's not a question if your system is going to be a distributed system. It will be. It's only a question of how distributed is it, right? The degree of distribution. And we saw
Yes.
that eventually when like microservices were all then the degree just exploded, right? And then I found myself at a spot that was marked by uncertainty. It's like I was just uncertain, right? I was constantly uncertain about my systems. I was uncertain about like what is going to happen next. What is going to happen in this case? I was just uncertain, right? And it is. I feel at my worst when I'm uncertain, because then I'm not confident, right? And it's a very like uncomfortable feeling. Right? And my initial reaction was basically, it's like, I want this confidence, I want certainty, right? And at that point, I started looking what is out there that grants me certainty. Right? And so my first touch point with that certainty was not deterministic simulation testing. It was formal modeling, specifically TLA plus, and then also to a degree alloy, and that basically means model checking. Right? And then I consumed, and at that time there was actually not that much material, and especially not material for like practitioners and beginners. But so I consumed everything there was, and a big part of that was the blog of Hillel Wayne. He did a lot of like beginner-oriented and practitioner-oriented models in TLA plus. And I realized it's like TLA plus is a thinking tool, or formal models as a thinking tool, right? It's just like all of a sudden gave me certainty, right? It's like I learned a certain way to think about systems, right? That what I like to call the distributed systems brain. And then I found other authors, like, for example, Martin Kleppmann, and consumed everything they wrote, right? And it's like I basically flexed my distributed systems brain and tried to develop that muscle. Yeah? And I enjoyed this. You see this model, and the model specifically states everything that can happen, right? And then it methodically explores the space, the behavior space, right? Incredible. Of course, behavior space, right? Behavior space of real world systems can be infinite, right? But the tools do a fantastic job to cover a large ground, right? And so they methodically, basically, and I say that like just quote unquote, methodically check everything that's interesting, right? So you can basically say they walk out the entire space, and then they tell you, it's like, if your system is correct, right? Is it good? And that was an incredible feeling, but unfortunately,
yes.
Now you know your design is right, yeah? But not the implementation, man. Yeah?
So it's almost teasing you. It's saying, it could work.
Yes.
If you code it perfectly, it could work.
Yes. Exactly. Exactly.
Right.
Yeah. So it basically now tells you, this model tells you, right? By checking its liveness properties, by checking the safety properties, it tells you that it is not impossible to implement this, right? But, which is good, right? That is good. But it doesn't get you any further than that, right? So then that is still, there's a lot you still have to cover, right?
Yeah.
That's when the uncertainty creeps back in.
And it came back. And then you feel even worse because you know it was possible, but we failed. But it can be done, but not by us.
It is almost like a difference from you never caught something, or you caught something but then it got away, right? So it's even more frustrating. Yeah. So exactly, it's like teasing you, right? But then you introduced me to the deterministic simulation testing, and then I consumed everything that was about that. So it's like all the YouTube videos from the folks that did Foundation DB, and then also the articles you recommended about Dropbox. And it was basically this promise that formal models made, right? It's like, we will replace this daunting uncertainty with nothing but certainty, right? And but now it promises this actually for the implementation, right? Not for a model of your system, but for your system, right? And then it's like, oh man, at this point you laid the perfect trap, right? You catch it and you keep it. That was my journey into deterministic simulation testing.
And I remember the first time we chatted. So it was a view stamp replication made famous sticker that we had made, because this was our consensus protocol for Tiger Beetle. This is what was scary for Tiger Beetle. It's like we have to write a distributed system. A consensus protocol is like climbing the Matterhorn or Everest. And, it can be fatal to, this is one of the hardest things to attempt, for me, that's how I saw it. And so I knew, I actually saw it. It was funny on Twitter today, James Cowling posting, who was one of the authors of the revised view stamped paper in 2012 with Barbara Liskov. But he was saying, I actually asked him for advice as I set out to climb the Matterhorn for Tiger Beetle. I said, James, fan of your work at Dropbox, we've picked view stamped. Any tips, please? I know this is not easy. He says, just have fun. It's a fun protocol. But then today on Twitter, he says, well, learning consensus is like learning to fight, so that you don't want to do it. And then, so I love that you picked the deterministic dojo, because that came to my mind. Well, there is a way to do it with determinism. But again, it was James and them at Dropbox. He was also, on that team at Dropbox doing these techniques. So, but I remember then you and I connected over view stamped, and I just showed you our deterministic simulator running in my terminal. And you said to me, but this is like formal methods or, model checking, but on the code. And I guess obviously there's a little bit of gaps, so some formal methods can actually go, you can annotate your code, and but it's not, it's still different. And I guess sometimes you can get formal proofs that the thing is entirely 100% correct. And obviously DST doesn't promise that. It just gives you confidence that as far as you are exploring the state space, it's not finding, what you tell it to find. So you also have to do all of that work. But I remember how it clicked for you as I showed you the probabilities in the simulation and the categories we were in. You said, but this is like model checking, but on the actual code. So.
It was an incredible moment for me because it's like the consensus algorithms is actually it's a perfect example. So when I started with distributed systems and when I heard about consensus algorithms, and that was before formal models, right? Before TLA plus, before Alloy, before Maude or anything else. You read about the consensus algorithms, right? And then it's like Raft is also a great example. So you read about it, and the Raft paper itself, right? The promise that Raft makes is not the consensus algorithm. The promise is going to be easy. It's not. It's not.
No, it's not. Yeah.
It's really not. And you try to think through it, right? And you try to think, and then it's like I watched the YouTube videos where people like explain the different steps and different transitions of, and it's like I always came up with one question that I like couldn't answer just based on the paper or couldn't answer just based on the video. That was always a situation I couldn't answer. Right? But then when I got into formal models and you look at and just like Raft, because of its popularity, you can almost argue that Raft is the hello world of formal models, right? So it's like every single formal model or a formalism that has ever been invented has been applied to Raft, because it's like everybody understands the problem. Everybody understands that the problem is really, really hard, and then you see it as like does the specification, the model, does that look good? Is that relatable? Is that tangible? Is that something that I want to use, right? And then you can work your way through the TLA plus model, for example, and at that point you start to understand. You get it. It's like you can just like, and it's not even that long, right? And you can go through it and you start to understand. And whatever question you have, you will find the path through the model, right? That is like, oh, this is how that works. So really, really very powerful. But at that moment, I'm sorry.
Oh, so just to jump in, I couldn't help, but I love how you said it's like a thinking tool. And I remember you saying to me, it's a great communication tool, for formal methods. But yeah, back to you, Dominik.
But at that moment, whenever I was talking about somebody or to somebody about like consensus, or whether it was Raft or any other protocol, but let's say like here's the model of Raft, right? Which is the tool proved this works, right? Here's the model of Raft, and then it's like, oh, should we implement it? And I was like, no, don't. Just don't. Do not implement this. It's like at that time, I know there was a very popular implementation of Raft. I believe it was a Golang library made by HashiCorp, where you could switch out the state machine, but they implemented the protocol around it. Right? And I always recommended people, before you ever think of implementing Raft, go to this repository and just look at the issues that are opened, right? And then you will see that these issues, right, they do not trace back to this model, right? So then you have some issue of a combination of this Golang version on this operating system in this version, right? Or then you have other situations when you say, it's like, hey, wait a second, how is that behavior of fsync? And we can think fsync gate and other things. All of that just is an implementation problem that does not make it into the model. Right?
Yes, I love that. It's formally proven, and yet almost every implementation of Raft is broken and can lose data and can enter split brain and have catastrophic cluster data loss. And there's a paper on this from University of Wisconsin-Madison from 2018, protocol-aware recovery for consensus-based storage. And this is the irony is, yes, there's a formal proof, but the proof wasn't in the real world, So if you run this code on physical hardware, the code is broken and not correct. The protocol is broken because the proof for the protocol didn't consider all the fault models. So it assumes that disks are perfect, And then again, as implementers, this doesn't really help us because again, look at the GitHub issues and disks do fail, So yeah.
And generally, you will not, right? You will not find this in the models, right? You just won't. You will not find it in the model. But eventually, there was the next thing that I came across then, and I listened to some presentation of Kyle Kingsbury, right? Where there's oh, wait a second, right? Now we are actually looking at the actual implementation. Right?
Yes.
And it started to feel like, hey, that's kind of close what the model checking tries to do, but on the system, but also not. So it's So it's definitely trying a lot of the things, right? That where you think, well, I wouldn't find it in the model, but I will find it in a real world implementation, right? So it comes and adds latency to the network, right? A lot of models can actually deal with that, right? Because they make very few timing guarantees. But then it does something, it manipulates the clocks on the node, right?
Oh, man.
Show me a TLA plus model that does that.
Yeah.
It will not.
Oh, yeah. I was also doing a bit of security work before Tiger Beetle, and I realized that hackers always go through the back doors. There's a little gap, a semantic gap between the system as modeled and the code as written, and hackers just walk through these doors and they chain them together. But coming into Tiger Beetle, I realized, well, distributed system safety is you spin that security coin around, and the same techniques that can stop hackers, just protecting your interfaces and closing the semantic gaps between model and code, yes, this also helps, And I guess I should say too, what you were saying earlier, you and I both love this principle of, end-to-end principle. So I think it's just this desire that we're how can we test the actual code, please? Because, proofs for consensus, ViewStamp, Raft, Paxos, dime a dozen. But how can we now, please, can we test the actual code end to end, in a real, that it works on real hardware. So I guess that's just what we were trying to do. And just to get some certainty, not even 100% proof, but
exactly,
it's better than what we had, so.
Exactly. And I love what you said. It's that's basically in a nutshell, right? So it's yes, it's formally proven correct. A dime a dozen in many different variations, but formally proven correct. Yet basically every implementation out there is broken. So it's oh my God, right? So that is just mind blowing. That disconnect, right? And then again, Jepsen was or is a very cool tool, right? That is tries to close the gap, right? But is short of the deterministic.
It's running the real binary too. It's it's the real thing.
It's a real thing.
It's extremely effective. Yeah.
It's a real thing, on real hardware, on real software, on the real operating system in the right version, on the real runtime in the right version, right? And it's incredible, right? It's incredible. It gets you far, right? But to be fair, deterministic simulation testing gets you a step further. And it's that step that closes the gap for me, where I have enough certainty to be actually confident.
And why is it, Dominik? What's the difference between simulation, where you now are simulating the real thing, or you're also doing fault injection. We've got, we're thinking about fault models. What are the guarantees does this program give to the user? We have network fault model, we have storage fault model, disks fail, process fault model, processes crash, clock fault model. Some projects even have like a CPU fault model and memory fault model, but I guess then you're into like Byzantine fault tolerant distributed systems, which, so it's kind of like, let's choose how hard we want to make it for ourselves. So Tiger Beetle, it's storage, network, memory, and clock and process, and then ECC is the answer. And there's also ways of detecting compute errors if you have a lot of assertions. But I guess so I guess this is the question: what's the difference? So we've got these fault models. We're thinking about guarantees we want to make. We're injecting now faults. We've got the simulation. But what's the difference? Because that is what Jepsen would do and is effective at that. But what's the little gap, you think? Because you and I have also done these techniques and we love them. They're so powerful. And yet,
the obvious answer, the answer that like anybody immediately, right? You tell somebody about deterministic simulation testing, anybody immediately understands, immediately grasps, and also immediately sees the benefit from it, is the reproducibility. And that is basically what you mentioned, right? You seed the Big Bang, and from that Big Bang, the entire universe unfolds. Meaning that if you seed yet another universe with the same seed, it unfolds exactly the same way, right? So the reproducibility is basically the obvious answer here. And the reproducibility is great, right? Because there's a difference between finding a bug and then fixing a bug, right?
Yeah.
Because if you do random simulation testing, right, you may find that bug, but you may never find it again.
And then it's also very reassuring because this actually happened to me. I wrote a simulator of a the pre-Tiger Beetle other system that I worked on, and it found a bug, and it could find this bug, and it took me a year to fix it.
Yeah.
And I knew it was there. So it's so reassuring, that your system's broken, and you literally, it takes a year. It actually turned out to be it turned out to be a buffer overflow in libuv on Windows if you use like an event notification mechanism, and if you have multiple very long directories, and if you have multi-byte encodings, and if you are combining NFD, NFC normalization conversion. All of that had to be chained together. And it took a year to figure that out. And that was actually the first C code I wrote, was to fix a buffer overflow in the BV, which is why I love Zig. But my very first C was, finding a buffer overflow.
That is jumping into the deep end.
Yeah, but that was when I realized, and coming into Tiger Beetle, I saw, there's this principle of determinism. That means I don't have to wait a year to fix it, because I can just replay it so quickly. Because otherwise you have to, run the simulator in real time, and it'll never get to that result because it requires these probabilities all to align. It's once in a year bug to find. But maybe we should come back to this. So it's all about reproducibility, replay. But what would you say to people that say, DST is not that great because obviously testing is all about state space exploration. That's the superpower. What would you say? Is that true?
I wanted to actually ask you. Yeah. So I take the I took the easy answer, right? I took the reproducibility of the board. Yeah. Then, right. And it is a fantastic property, no question. Because exactly, we don't have to wait a year, right? But there is more to deterministic simulation testing that is not as obvious as reproducibility.
That's it. Yeah, so I think, shall we leave that as shall we build some tension here? So what's DST really about? Even beyond being deterministic, being reproducible. Is that where we're going?
That's totally where we're going. Unfortunately, I didn't line up any sponsors for that video because otherwise I could play an ad now, right?
This would be the time for the ad. Is that like, but to tell everybody that DST is not about having reproducible simulations and fixing bugs faster.
Exactly.
Okay.
But unfortunately, we don't have any ads lined up. So
okay, so let's imagine that we've got a movie, Dominik. So like if DST is a movie, you're saying that now for the first time we can watch, if we like a movie again, if we like a movie, we can actually watch it again. We can replay the movie. And
that's nice.
Okay.
Yes.
Yeah. And we can replay it again and again, and we can now add, logging and fix it. But I think this is the thing that surprised me, doing this with Tiger Beetle, is that's how I see DST. It's a movie that you can replay. But before that, actually, it's a movie that you fast forward. And so you've got the movie, and you fast forward it, because even time becomes something in your model that you can accelerate it. DST is all about taking the physical, random, non-deterministic stuff, network storage, time, and you make that all logical, so you have a logical clock that you tick, and in this whole simulation you control everything. Even the clock on the wall in the matrix, you just spin that faster. So now actually your simulation is a movie that you can rewind, yes, but the real superpower, I think, is that you can fast forward that movie to see if it has a happy ending. And if it does, you just forget that movie and you watch a new one. Okay, happy ending, okay, forget it, a new one. And each of these are just little seeds. And from that random seed, you have a random stream, and you use if-else decisions like 50% probability, let's do some fault, or, and you can, there's lots of techniques, we can come back to that. But I think this is the real thing, is that it's a movie you can fast forward to find bugs. If the movie has a sad ending, it's like choose your own adventure, then you can replay and see where it went wrong, butterfly effect, and make sure it doesn't have that.
Oh, that's good.
Yeah. But I think this is the other thing, is that this is just, determinism is a principle. So DST is really, what we're saying is, we believe in testing. Yes, we believe in, and all the literature of all test techniques, for good testing, yes. Simulation, yes. But let's also make our movies fast forwardable and replayable. So it's just complementary, really, I think, to all the literature on state exploration, minimization. All these things are all compatible with DST. So I think maybe sometimes, there's a misconception that, DST is a bit overhyped because, state explorations where it's at. Why not both? We don't have to be XOR. Determinism is a principle, and we should be bringing it in, because I think it's a good idea, yeah. So I think that's kind of the most surprising thing for me, is that it's a very good philosophical principle, and like philosophy, you can now do things in the matrix, yeah. What are your thoughts on all of this? What shall we dive into a bit more?
I very much agree. So the way, so with reproducibility out of the way, right? Where we say, yes, it's now reproducible. We can look at like the other enablers, basically. It's like, what does DST do for you? Right? And I think there are multiple levels to that. There's like one more subtle than the next. So the first one, the most obvious one, is reproducibility. The next one is where DST enables scale, and DST enables scale across space and across time. So what do I mean by that, right? So we can view a system as a generator of behavior, right? So it's like I have a system and I tell the system run, right? And then the system generates a behavior, transitions from state to state to state to state to state. So turns out though, systems have a happy path, right? And that's why we have a word for it, happy path, right? So systems have a happy path. So if I just tell the system to run, right, just like it's going down its happy path, right? And if I tell the system to run 1,000 times, the chances are very, very high that it goes down its happy path like 999 times, right? Because it's just very, very rare that I accept a new network connection in the exact same moment that like a configuration reload is triggered. It just happens very rarely, right? But behind this specific path through the system, there may be a bug, right? That's why I love this word Heisenberg, right? So from the Heisenberg uncertainty principle, yeah? So comes out of nowhere. As soon as you try to look at it, it's gone, right? So then it's like you measure it, you can't see it again. Yeah.
Yep.
So, but with DST, right? And it's like, and again, it's like you seed the universe, right? You seed the universe. You seed it with 1,000 different seeds. It goes down this particular path, right? And it's not the same path that the next seed is going to generate. And it's not the same path that the next seed is going to generate. So if I just kick the system into gear, and 1,000 times, it's like chances are high the system is just going to go down like 1,000 times, basically the same path. But with DST, I have a chance to actually, if I kick it into gear 1,000 times, to go down 1,000 distinct paths. Right? So that's what I think is this idea of it scales across space. Right?
State exploration, yeah.
Yes, exactly. It's a state exploration. The other thing is this idea of scaling across time. Right? It's also what you said. Systems are time dependent. Right? There's like, we have time. Distributed failure detection usually depends on timeouts. It's like detecting message loss depends on a timeout. If you need to test something like rate limiting, here you have a time interval, right? So real systems depend on 24 hours. You need 24 hours, right? So, but with DST, if you can virtualize time and you want to test the system over 24 hours, depending on your test setup, but it's like if in doubt, it's less than a second, right?
That's
and
it.
now, right? And now you multiply that. It's like scaling across time or scaling across space, scaling across time. And then you see, it's like, what is like the simulated runtime? How long would I have to run this system on how many machines to get the same experience, the same coverage that I get here in a mere hour? It's incredible. Is just incredible.
Yes, I've actually chatted with people, and they've had this misconception about DST that it's slow because you run it logically single-threaded and there's no multi-threaded parallelism. And then I said to them, but you know that you can make time, this physical time, you could make it logical and speed it up in a while true loop, and you can go 700 times faster, so you don't need. And then they're like, okay, wow, never thought that you can fast forward the movie again, So like you say, like scales in space and time. It's that kind of philosophy, you take the physical and make it logical. And determinism encourages you to think like this. And then now you look at your event loop in Node.js or libuv a little differently, your timers, timeouts, frequencies that are every 1 second. Doesn't have to be a second, just if you simulate your clock, spin it faster. So I think Tiger Beetle, we get like a 7. We've worked this out roughly. It's probably changed, but it's roughly like a 700x speed up over physical time. So 1 second gives you 700 seconds. And then you can run this on parallel. You take your single-threaded simulator, but run 1,000 of them. So we do have like 1,000 dedicated CPU cores. They run 1,000 simulators, different seeds. You can also do better than random. So you can use different distributions like swarm testing. You can so much. So again, it's all complementary, I think, to existing techniques. But it's this principle that is so powerful.
Yeah, absolutely. And for me, this is, again, reproducibility is like the most obvious, right? Everybody like carries that on their sleeve when they say DST, reproducibility. Great. The next one is a little bit more like subtle, right? Where it's like you already have to like think about it a little longer or have a bit of a longer conversation. That is like this scaling across space, state space exploration, scaling across time, speed of time. But then there's yet more, right? There's yet more to come, and that is, well, for deterministic simulation testing, right? Your system has to be deterministic, and
Yes. I guess we should say this is the sad news. If people are getting excited, someone I saw in the chat wants to ask, can you apply DST to Spanner? Or should you hire 300 engineers in QA?
It's like it's a good question, right? If you don't have the time to do it right the first time, right? Do you think you have the time to fix it over and over again? That's a good question. Yeah?
I mean, it might, at some point it might be quicker just to rewrite it and save on the few hundred test engineers.
But as we know, lately, there's also you can get determinism on like different levels, right? So there is, for example, antithesis who provide a deterministic hypervisor, so that you can run basically what we can consider an otherwise non-deterministic system in a deterministic way. And that has a lot of advantages in and of itself, because of course now you can say we can apply this to a pre-existing system. But in addition, this is like I am a big fan now, big fan of deterministic simulation testing, basically on the application level. You build your application with deterministic simulation testing in mind, because it is a transformative experience. Also, not just for ourselves, but for our system and for the code. The way that it is built. And the first time I implemented deterministic, which is basically for Resonate. So it's like me and my co-founder, when we started we had the luxury of starting on a green field, right? So we started implementing the Resonate server with deterministic simulation testing in mind. But it was a transformative experience beyond the testing, because it turns out that also DST is a reasoning tool. Also, DST is a reasoning tool about your code. So the first thing you need to do if you want to do DST, you need to take control of the event loop, right, of the scheduler. Nobody ever takes control of the event loop, right? We just throw something onto the Python event loop, onto the Node event loop, onto pick your favorite platform, and throw your code at the event loop. Right?
Yeah, and I know you really love Go, and you had a fight with the scheduler there, right?
Yeah. Love is a strong word, but it's like, so we did choose Go for the we did choose Go for the Resonate server. And if you do that, right?
Good choice, by the way.
It's operational heaven, right? Because out comes a little binary that is self-contained, and off you go. Yeah? But if you're looking for DST, then it's like it's development hell, right? Because it's like Go doesn't provide you any of these capabilities. Definitely not out of the box, right? You have a set of Go routines. That's basically the main unit of abstraction, right? Or the main unit of decomposition. So you have a set of Go routines, and you throw that just like at the runtime, right? And you do not know the cut points, the slice points. You do not know. It's like, is it gonna run these 2 lines? Is it gonna run these 8 lines of code? You also don't know that may change at any point in time, right? So you have this massive, like, non-deterministic tree of possibilities that if you have to, right? So now you also communicate with channels and messages over channels, whereas like Go says this is the main way of like synchronizing. Where it's like where you prune this tree again, right? Where you come back in. Turns out even for Go, that wasn't true, right? So now we also have mutexes and semaphores and whatnot. So first off, we let the thing explode, right? It's like completely explode, and then we try to rein it back in certain situations, right? So it's like, oh, but
Yes.
in this case, let's bring it all back in, right? And with DST, if you implement it to be deterministic on an application level and you take control over the event loop, one thing that happens is it's like what manifests is atomic stretches of your application, right? Because now you also have to implement not preemptive, but cooperative concurrency control.
Yes.
And now you have atomic stretches. You see that. Your system promises you that, right? It's a promise. This will never be interrupted. I'm not promising you that this will run before that or this will run before that, but I promise you, once this happens, it will run to completion before something else will happen. That's amazing. It's a transformative experience. Your code, your system gives you so much more guarantees, so much more to latch onto, to reason about the possibility of your system. Right? This wild behavior tree is from the very beginning nicely pruned like a bonsai. It's fantastic.
Yeah.
It's absolutely fantastic.
Yes. It's been my experience too. I thought, started off with coding, get into testing, and figure out how can we condense testing time, because that's 9/10 of the it's the reason why consensus normally takes 10 years to get right, and then you still have all the issues with a non-deterministic system. So like let's engineer that problem. Okay, determinism, and then you have this wonderful discovery that my code got better. The design got better. It's a forcing function. I've got a first-class event loop. I'm thinking in terms of like the scheduling I want, and I think languages in future are going to get better because determinism is now a thing, and so yeah. But even with Zig, we didn't use Zig's event loop because we wanted to control. But Tiger Beetle's design got better, the architecture. So I love that too, that it's a forcing function for good design, because it forces you think of your guarantees that you make. Think about what is correctness, what are the faults we need to survive. Make a matrix of what network storage, etc., and then test that and on the real code, and so all these things just get better, being more explicit. I did think one thing too is that. What's curious, I think, with Resonate, you knew from the beginning DST, and I gather, how, for you, like how quickly did you actually have your simulator up and running? Like, were you coding and then after a while you wrote the simulator, or was it like upfront and you already had a simulator and then you were coding in it?
Upfront. We immediately started with the simulator. The harder part was for Golang, right? To find an abstraction, a unit of decomposition, right? That is not the Go routine. Find a unit of decomposition that also provides us a good developer experience, right? To express ourselves in. So what we ended up doing is we implemented a kernel, which is a scheduler, and instead of Go routines, we use coroutines, right? And then so we implemented coroutines on top of Go routines and channels, and we interleave them so that only one Go routine at a time can be activated by the Golang scheduler. Therefore, we have full control over the scheduling.
Okay, so you were careful to take everything that's physical or non-deterministic and abstract it logically, so that you have a complete logical piece of code.
Correct. Yeah. And then we were also inspired by IOU Ring to basically say we have this deterministic core, right? And then we hand something out into the non-deterministic world, and this eventually comes back and it's phased back into the deterministic world, right?
Yes.
And that is basically all we had to. But what we had to simulate them was basically a scheduler for the coroutines.
Yes.
And since that doesn't allow any concurrency, that's super straightforward. And then we had
Yeah.
to simulate basically the subsystems, what we call subsystems, where we hand I/O requests to the outside world, had to simulate that. And then everything came together very naturally.
That's also what I love about it, is that it forces you to think where the if we had a T-shirt, I would have a T-shirt that says software should be logical. Because if your software is truly logical, and I mean logical, that it's not non-deterministic, but if your code is truly logical, you can do DST. But if your software is illogical, let me not say that, but with great respect, but I think software should be logical. And so DST, determinism, forces you, if you're architecting your system, designing interfaces, where are interfaces touching the physical world? Think very carefully there. And just, I found, 3 good tips in Tiger Beetle. Minimize surface area of the interface, make it very narrow. Then, because, the more surface area, the more state space explosion you're going to have to try and hunt down in your testing later. So, people often say, like, how do you do state exploration? And in Tiger Beetle, we're like, well, design it away in the first place. Like, try and reduce dimensionality in the first place, narrow those interfaces in what the state explosion they will allow, because you will pay for it later in your testing, So narrow the logical to physical interface. Wherever you touch the physical world, narrow those points. Then align them in terms of your fault models. How can that physical network or storage fail? Make sure your interface is aligned. So in Tiger Beetle, if you write to the disk, we're not trying to make the interface like POSIX, because that would be a nightmare, the state space explosion. So don't do that. Don't be careful where you model your where that logical physical translation happens. In Tiger Beetle, if we want to write to the disk, the function is write sectors. Here's a buffer at this location. There's a callback, and that's it. There's no error. So it doesn't promise anything. Maybe it wrote it, maybe it didn't, but that's how disks work. That's now explicit to the logical program. The logical program is now responsible for checking and handling disk corruption, writing to the log. So it's like minimize your interface surface area, design dimensionality, try and save yourself from state exploration later, align to the fault models, of that particular physical interface, and promise nothing. Like, the interface should make no guarantees. The less guarantees you make, the easier it is, down the line, because that's just how the real world is. Don't get your hopes up, Otherwise we doing formal proofs, like back in the day, but we're not being realistic. In the real world, everything just fails. Even where it promises not to, it still fails. So yeah, I think that's also, that's just been some of our experience. But Dominik, guess how long it was for Tiger Beetle? Like, do you think we started with the simulator, or when, how long into the project until we had the Whopper?
I'm sorry, the audio was cutting out. I could not understand your question. What did you say?
Okay, so guess for Tiger Beetle, did we start with a deterministic simulator, or when did we create it? Like, take a guess.
Oh, I would think. Are you asking when you started to include the determinism into Tiger Beetle, or when you implemented specifically the Whopper?
When we actually started testing it, like when did, because I think with test-driven design, people think it's like, you write the test first. So maybe in DST, you have to build the simulator first from the very beginning if you want to do this. But, for Tiger Beetle, guess when we actually built the simulator, when we actually just started testing.
That is a very good question. I never thought of that. Okay, now the way you asked the question is leads me to believe that it was not the very beginning, but it must have been pretty soon, though. Yeah.
It was actually at least a year. So I think maybe this is, I say this because I hope it's encouraging to people. If you start with that T-shirt, software should be logical, principle of determinism. If you understand these ideas from the beginning, I mean, this is what we planned Tiger Beetle in the design, thinking of all these things in the very beginning. We only wrote the simulator a year later. It was a whole year.
That is pretty late.
So it was a year of work. You know where you're going, you know the principles, and we were quite comfortable. Like we go for a year. Took 3 weeks to actually create the first version of our Whopper simulator, View Stamped Operation Replicator, tribute to Wargames Whopper. So it took 3 weeks to make the simulator. It didn't take long, just 3 weeks to write our test code. And then we ran it and then found 30 really like Heisen bugs in 3 weeks. So each day we were fixing 5 bugs a day. And these were bugs that sometimes, to reproduce, they require 0 millisecond round trip times on the network. Each of these bugs would have taken a month, 2 months, but we like fixing 5 a day. This was just the first 3 weeks, after switching on the simulator. I mean, yeah, so and as you develop new code, you're always finding bugs. But I think this is the idea, is that DST doesn't have to be TDD. You can just have the principles in mind, write your code. You're going to re-architect a lot of your code. So probably, you can benefit from letting that simmer a little bit and churn, and then you'll know when the right time is to give you velocity. Then you switch on the simulator, and then, yeah.
We had a very interesting experience in that regard, because we started with DST, right? But because of the principles that you mentioned, this the connection from the logical to the physical. Right? So my co-founder and I, eventually we called it not the distributed systems brain, but the DST brain. So if you work with DST, right, you start anticipating before you even run the simulator, right? Because you basically, everything is very explicit now. This is a scheduling point, right? Here the scheduler may choose something else. This is an I/O point. So this is concurrency, non-determinism introduced by concurrency, right? This is an I/O point. Here, the non-determinism introduced by distribution, basically partial failure, right? Here, a request may either be successful or it may generate a failure, right? So now it's everything. All of these points are incredibly obvious, right? They turned out to be so obvious that our DST didn't find a bug. It's like my co-founder David kept texting me all excited and was like, oh, there's something else. And then I was like, did the DST find it? I was like, yeah. Oh, no, I just thought of it. I was like, for the love, man, stop. I want the DST to find the bug. Yeah. So the DST made it so obvious that we actually, from the very beginning in the Resonate server, had a very high level of quality, and the DST just found the most outrageous things. If this request and this request is basically duplicated and comes in the very same batch, but from 2 different clients, something where it would just basically never happen, right?
It's like the perfect hacker. It's chaining 8 exploits together, and each of them are incredibly rare, but it finds it,
and then it finds it, correct. So we were fixing bugs from the very get-go. Well, it's in a million years, I don't think anybody who deploys that system would actually ever see that bug. Right? No, but we were fixing these bugs from the get-go. An incredible feeling.
Yes. I'll never forget the feeling when we switched on that simulator. I remember listening to Kings of Leon crawl, that was playing, and the simulator was just burning CPU, and I coded for many, many years, and then you finally determinism, the principle kicks in, and I would know. I mean, at Tiger Beetle, we would never build any system without this principle. I think maybe we should give people some hope, though. What if you've got a big system that doesn't apply this? What could you do? is there such a thing as a deterministic computer? And I think neither of us have shares in antithesis. So, so we really like. It's just they've also pioneers from Foundation DB, but they actually built a deterministic computer. So if you have a non-deterministic binary, put it in the deterministic computer, and you can wear the T-shirt. Software should be logical. And they do a ton of state exploration and testing. But then, what would you say, Dominik? Like, should you only have like an external audit function, like a deterministic, auditor that, like antithesis, or should you only have an internal audit function, like your own simulator? What would you say?
I would go for both, because the reason for that is that it's like, first off, this transformative experience, right? So it's like it transforms how you design your system, and it's like the implementation of your system will be different and better. So I do like this application level DST, and taking control of the event loop and taking control of your failure models, and also the scheduling points and failure points is incredible in terms of system design.
Yes.
But that doesn't preclude that you can also run that now in a deterministic computer, right? Because the only thing that happens is you can only find more. You can't find less, right?
And it's like, Will Wilson said to me, Swiss cheese model. If you have, if you can have two deterministic simulators, great, because now if one misses something, the other finds it. Swiss cheese model, defense in depth, another way to stop hackers. Just if you're going to be a bug in Resonate or Tiger Beetle, good luck, but you'll have to get through two simulators. Then I think at that point it's like, well, maybe three, but I think two is enough. Internal audit, external audit.
I could actually also spring, and I also have no shares or no stakes in Jepsen, but it's an application level simulator, platform level simulator, like the deterministic machine, and then it's like a Jepsen test together.
Absolutely.
For the sheer realism that Jepsen is able to produce, right? Very, very realistic setups of systems that Jepsen is able to produce, like starting from the software version of that operating system, right? And the software version of that compiler that you use, and the software version of that runtime that you use. So very realistic settings that it can. And at that point, I think you basically reach the Mount Everest of test. It's just not going to get any higher at that point. It's like, if you have the resources and you can formally prove every single line of code, good for you. I don't think we'll ever get there. But, so it's like DST and Jepsen in combination, that is something that is doable, and the return on investment is definitely there.
I'm so glad you said that, because that's kind of also how we think at Tiger Beetle. Like, Carl's skill is phenomenal. Like because you see, this is the other thing, is that it's great to have a deterministic simulated world, but you need creativity, you need the human, you need, are we actually doing a complete model checker? Like, how are we covering the whole product surface? Everything this thing. And Carl is just great at that, at like the actual, it's just phenomenal. So I think that's really, I think this is the way to do things. Have DST, then use Jepsen, and at Tiger Beetle we kind of thinking, maybe I should say this, but we've actually written a non-deterministic simulator ourselves. It's called Vortex. So we've got a blog post coming soon with details, but so this is kind of where it's at, I think, is that you do 90% of your local development on your machine, DST. But there comes a time where you want defense in depth, and a non-deterministic simulator can be great. What you can do with that. It's like a canary, because you should never be finding bugs there. If you do, there's something wrong with the automated deterministic CI.
Yes. Yeah. Very, very well said. So that would actually be if Jepsen and I'm already now super excited to read that blog post, but if Jepsen or something like Vortex finds a bug, I would by no means jump on fixing that bug. I would immediately jump on the question, why did the simulator not find it?
And that's what's so amazing, the feedback loop now that you get. And I think this is the other thing, it can take you a week or 2-3 weeks. I mean, it took us longer at Tiger Beetle. I always feel slower and slower, but like it takes you 3 weeks to like set something up if you have the principles in place that we've shared. But then you never stop investing in that, because whenever you're just making your simulator more and more protocol aware. And I think this is the difference with the deterministic computers, that if you have your own in-house simulator as well, and an external audit, your own simulator can get you can start pushing things to the theoretical limit of your protocol. The fault injection can be, and that's what we do with Tiger Beetle. So, and you just keep investing in that. So exactly as you say, you find a bug. The question is, I'm not even going to try and fix this under the non-deterministic simulated vortex. Why didn't the Vopper pick this up? And this is exactly what we do at Tiger Beetle, which is really fun, So,
and that is actually probably also, since we're a little bit over time, a very good closing thought is that we also basically pay tribute to the evolution, right, of deterministic simulation testing, because as you said, once you adopt that, you keep improving the deterministic simulation testing itself, right?
Yes.
And that just keeps improving the systems many times over, right?
And
so
and it's just complementary with everything, like you said, it's evolution, but you still use Jepsen, all these techniques. It's just complementary, So that's, and I love, like you say, I love it to like pay tribute, all the pioneers, and we also just really lucky, like lucky timing, that someone else, CJ James shared this idea of determinism.
Yeah, very true. Standing on the shoulders of giants.
And having fun.
and having fun in the process. It's like I was just lucky. I saw the sticker of the fuse stamped replication. That's what started this journey.
Yeah, no, me
Super
too.
cool.
I mean, imagine if I hadn't chatted to you. I mean, there's, as you know, there's like impact on Tiger Beetle, like that sticker, all comes back to consensus, which is only possible with DST. So, yeah.
All comes back to consensus. Okay, so I guess eventually we just have to have James on the call as well.
Yeah.
Awesome. Hey, thank you very much. Thank you very much, Joran. That was really, really fantastic. I enjoyed that a lot. Thank you, everybody, for joining. I saw that there was like lots of activity in the thread. The talk was so engaging. I couldn't jump on the questions, but I think it's like the participants also chatted with each other. So thank you very much for that, for everybody who jumped in and posted references and like answered questions that other people in the chat and in the ecosystem had, right? So it's like just all here, and then we're paying it forward, helping each other. Super cool. That's a really fantastic spirit. And if you have any questions, it's like of course I don't want to speak for Joran, but from personal experience, he's very open and very helpful. So I think it's totally cool reaching out to Joran. It's absolutely cool reaching out to me. So if you wanna know anything, if you wanna brainstorm, if you wanna just bounce off ideas or have questions, please don't hesitate and contact me. You can either find me on Twitter, or you can join the Resonate Discord. And Joran, what's the best way to reach out to you?
Twitter DM, email, Joran at Tiger Beetle, and yeah, second everything Dominik says. What is the Vulcan salute, Dominik?
The Vulcan salute, that should be this, no?
Yeah. So I guess we say live long and prosper. and keep
Oh
your software
yeah, live
logical.
long and prosper. That's right.
Yeah, keep your software logical. Yeah. No, yeah, with any time, always great to chat. So and yeah, so we love to help people out, and I like how you say pay it forward. So as people have done to us.
Exactly. Exactly. Very cool. All right, then it's like the next deterministic dojo scheduled for February 26th. Yeah, but until then, yeah, there will definitely be a lot of chatter about a DST outside of the deterministic dojo.
Okay, I know what we'll talk about next year. There's something new on the horizon. Like what's the next thing? Yeah.
What is the next thing? Are we already talking about it this year?
I think we'll have to speed up time and find out. But
Nice.
it'll be interesting
And
to
that,
see. What we've got. Yeah, cliffhanger.
but it's just like a cliffhanger. But I'm sure that movie has a happy ending. So that's a good part.
Yeah. No,
All right. So then, thank you very much, everybody. Thanks again, Joran. And then I see everybody virtually and hopefully soon. Thank you.
Thanks so much, Dominik.
Bye-bye. All right.